Hello everyone, my name is Prakash, belongs to the Department of Physics and Electronics, K.B.N college. Okay. In the last session we have discussed about the ghost wave optics, and then we have discussed about the first unit, what is interference of light. Okay. In today's session we are going to see the next one, which is called the diffraction of light. What the diffraction means, what are the types of diffraction involved in this. And coming to the contents of the today's session, we're going to see what is diffraction, what are the types involved in the diffraction, then what is interference, and what are the differences between interference and diffraction, and what is Fraunhofer's diffraction and Fraunhofer diffraction due to single slit, plane diffraction grating, how the wavelength of light can be estimated by using a plane diffraction grating by using normal incidence method. Then what are Fresnel's half period zones, how can it will be useful in order to construct a zone plate. Then what is a zone plate, then what are the comparisons and we can say similarities and dissimilarities between the zone plate and a convex lens. Okay, without wasting much time, let us get into the session. If we see this figure, when the light beam falls on a glass prism, it will be splits up into 7 colors. You can see here, Vibgyor. What does it mean, or why it will happen? We'll see. Coming to the diffraction, it is a normal phenomena that the waves bend round the obstacle placed in their path. Okay, when there is an obstacle in their paths, the waves bend around that obstacle. This phenomena is called diffraction. For example, if you take a water wave, sound waves, suppose let us take the example of a water wave which is coming from a small outlet or a small hole. It will spread out in all directions if the water flowing in that hole, okay, as if it is originated from that hole. Okay, this is the example that the waves will bend around an obstacle. This will be happens in the sound waves also. Okay, the diffraction says that is the amount of bending will depends upon the size of the obstacle and the wavelength of the light. Okay, what is the size of the obstacle we are keeping and the wavelength of the light. Okay, we can say wavelength of the light if it is a water waves. What is the actual definition of diffraction? When the light falls on obstacles or of small apertures whose size is comparable with the wavelength of the light. The size of the obstacle should be comparable with the wavelength of the light. There is a departure from straight line propagation. This bending of light is called diffraction. Diffraction produces bright and dark fringes known as diffraction bands or diffraction fringes. As you have seen in the last class, that interference will produce interference bands or interference fringes. In the similar way, diffraction will produce diffraction bands or diffraction fringes. In simple words, we can say that the diffraction means bending of light ray when it passes through an obstacle and it deviates from its rectilinear propagation of light is called as diffraction. Okay? Bending of light ray when it passes through an obstacle and deviating from its rectilinear propagation of light is called as diffraction. Then coming to the types of diffraction, before going to the types, we need to know, in order to study about the diffraction, you need to keep an eye on 3 factors, that is source, and the next one is the aperture, and the third one is the screen or telescope. Okay? 3 points are source, where the light is going to come out, and the aperture. The third one is a screen or telescope. Okay, these are the 3 factors you need to keep an eye. Now coming to the types of diffraction, the first one is about the Fraunhofer's diffraction. In this class of diffraction, source and the screen are placed at infinity. The source and the screen are placed at infinity, or we can say effectively from the large aperture. Okay. In this case, the wavefront which is incident on the aperture of an obstacle is plane. Okay? The wavefront is plane when source and screen are placed at an infinity from the aperture. Now coming to the next one, Fresnel's diffraction. In this class of diffraction, source and the screen are placed at finite distances. Okay. In the last class, Fraunhofer diffraction, we have seen that the source and screen are placed at infinite distances. Here we are seeing that the source and screen are placed at finite distance from the aperture. In this case, the lenses are used for making the rays parallel. But in case of Fraunhofer diffraction, we are using convex lens in order to make the rays parallel. But in case of resonance diffraction, there is no use of any lenses to make the light rays parallel. These incident wavefronts are either spherical or cylindrical. These are the two diffractions based on the three factors: source, screen, and the aperture. Now coming to the what are the differences between interference and diffraction? The superposition takes place in interference. I am talking about the interference. The superposition takes place between the two separate wavefronts originating from two different but coherent sources. They should be coherent. Means that their two light waves should have a constant phase difference between them. Okay. But coming to the diffraction, the superposition takes place between the secondary wavelets originating from the different points of the same wavefronts. They are originating from the different points of the same wavefront. Coming to the interference, the regions of minimum intensity are usually almost perfectly dark. Minimum intensity is perfectly dark. This is due to the fact that the amplitudes of the interfering waves are equal. Why? Because they are coming from the same light source. Okay. But coming to the diffraction, the regions of minimum intensity is not that much dark. They are not perfectly dark comparing to the interference. Coming to the interference, the fringe widths may or may not be equal, or you can say they are not uniform. The fringe widths of different fringes are not equal here. The fringe widths of different fringes are not equal here. The maxima are of equal intensities in interference. The maxima is of equal intensities, but coming to the diffraction, the different diffraction maxima are of varying intensities with maximum intensity for the central maximum. Okay, it will be having the maximum intensity for the central maximum in the diffraction pattern. But coming to the interference, the maxima are of equal intensity. They will have an equal intensity for the maximas. Then going to the next topic, Fraunhofer diffraction, or you can say the Fraunhofer diffraction due to single slit. Okay, here you can see the diagram. Let AB is a slit of width E. It is a slit of width E which is placed in parallel to the plane of the paper. It is placed in parallel to the plane of the paper. Then W and W dash, here you can see W and W dash is a plane wavefront which is emitting a light source of wavelength lambda. Okay, AB is a slit and W dash is a plane wavefront. Then according to the Huygens and Fresnel, every point of the wavefront in the plane of the slit is a source of the secondary spherical wavelets which will spread out in all directions. They will spread in all directions. Okay. Then by using, here you can see, by using a convex lens, we can make the divergent beams to make it fall on the screen at P0. Then P0 is a, or you can say P0 is a central bright fringe. Central bright fringe. The secondary wavelets traveling at an angle theta with the normal at a point on the screen. Okay, at a point P1 on the screen. Here you can say that P1 is either of maximum or minimum intensity. It will be depending upon the difference between the secondary waves. Okay, it may be maximum or it may be minimum, but it is depending upon the differences between the secondary waves. Okay, then coming to this one, so-called resultant intensity. Then coming to the resultant intensity at the point P1, you can say the phase difference is given by 2 pi by lambda, where lambda is the wavelength of the light source W dash and E is the width of the slit. So 2 pi by lambda times of E sine theta. The width of the slit is divided into n equal parts and the amplitude of the wavefront from each part is A, where A is the amplitude. Then the resultant amplitude, or you can say the resultant amplitude capital R, is given by NA sine alpha by alpha, where which will be equal to capital A sin alpha by alpha, where Na is equal to capital A. So we know that the intensity is given by square of the amplitude. So I is equal to R square into A square sin alpha by alpha square, okay, which will give the intensity. Then coming to the principal maxima, okay, the condition for principal maximum, you can say R is equal to A alpha times of alpha minus alpha cube by 3 factorial plus alpha power 5 by 5 factorial alpha power 7 by 7 factorial. Okay, if all the negative terms vanish, the value of capital R will be maximum, that is alpha will be 0. If you keep alpha is equal to 0 here, then the sin theta should be equal to 0. Sin will be 0 only if the theta is equal to 0. If theta equal to 0, then sin 0 will be 0. So the maximum value of R is A. Okay, the maximum value of R is A. We know that square of the amplitude nothing but A square is the resultant intensity. The maximum is known as the principal maximum. This maximum is known as principal maximum. Okay, and going to the next one, the minimum intensity positions. The intensity will be minimum when sin alpha is equal to 0. The values of alpha satisfies the equation alpha is equal to pi e sin theta by lambda, which is given by the relation plus or minus m pi, where m is equal to 0, 1, 2, 3, so on times of pi. In this way, we obtain the minimum intensity on either sides of the principal maximum. We can find the minimum intensity on either sides of the principal maximum we can observe. Coming to the secondary maxima, in addition to the principal maxima, there are weak secondary maxima between the equally spaced minima. Okay, there are secondary maxima between the equally spaced minima. These maxima are obtained when sin alpha by alpha becomes maxima. Okay, these maxima are obtained when sin alpha by alpha becomes maxima. Then we will see about the intensity distribution graph. You can see here this graph shows the variation of the intensity with alpha. Okay, the diffraction pattern consists of a central principal maximum here. The diffraction pattern consists of a central principal maximum occurring in all directions of incident rays. They will be occurring in all directions of principal or incident rays. Going into the next topic, plane diffraction grating. What is a plane diffraction grating? An arrangement of large number of you can say in simple words, an arrangement of number of parallel equidistant slits. An arrangement of large number of parallel equidistant slits is called a diffraction grating. Okay, is called a diffraction grating. If small e is the width of the slit and small d is the difference between the separation between the two slits, then the combination of width of the slits and the separation between the two slits d is called the grating element. The grating ruled on a glass plate is called as transmission grating. The grating ruled on a glass plate is called transmission grating. If capital N is the number of lines per inch, then n into e plus d, which is called as grating element, is equal to 1 inch. We know that 1 inch is equal to 2.54 centimeters. E plus d is given by 2.54 divided by capital N. So in order to find the wavelength of the light by using a plane diffraction grating, the formula is given by 2.54 times of sin theta divided by small n into capital N, where n is small n is order of spectrum and capital N is the number of lines per inch on the grating. And this is a spectrometer, okay, where this part is called as the collimator and this one is called as the grating stand, where we can place the grating or prism, and this one is called as the telescope. Okay, collimator, grating stand and telescope. So here we can see in this diagram we placed a plane diffraction grating on the prism table. And in order to find the wavelength of the light by using a plane diffraction grating using normal incident method, you need to make some adjustments initially. The first point is The eyepiece of the telescope is focused on the cross wires. The eyepiece of the telescope should be focused on the cross wires. The second point is the collimator and the telescope are adjusted for the parallel rays. The collimator and you can see here the collimator and the telescope are adjusted for parallel rays. And the third one is the grating is placed on the prism table in such a way that the light coming from the collimator should fall normally, or you can say they fall normally on the prism table. These are the three adjustments you need to make while doing this experiment. If T1 you can see if in T1 position the direct image of the slit is seen at crosswise of the telescope. Okay, the telescope is now turned for the 90 degrees angle. Now it came here, which is exactly 90 degrees with the collimator. Now the grating is mounted on the prism table at the Z1 position, which makes an angle 45 degrees with the collimator. Now the slit or the prism table is made to rotate. Okay, see, while the grating surface coincide with the crosswise of the telescope. Now table is rotated about a 45 degrees angle so that the grating comes to the position of Z2, which means that it is parallel to the collimator. So in this position we need to find the wavelength of the light. After this adjustment, the telescope is now turned till the first order spectrum is observed on either sides of the telescope. In left and right you can see first order and second order. It should be rotated in both the sides. The telescope is so adjusted that the line falls on the intersection of the crosswise and the readings of both the verniers are taken. The telescope is then turned to the other side of the direct image, and the corresponding readings for the same line in the first order and are again taken. Okay, the difference between the two readings, okay, the difference between the first order on left side and the right side will give the 2 theta reading for that line, so from which we can able to find the angle of diffraction theta. So this experiment will be repeated for the second order spectrum also. You can see here on both the sides of the telescope, from left side and right side also we need to repeat the same experiment. We need to find the angle of diffraction theta. So by substituting the values of theta on this formula, we can able to find out the wavelength of the incident light by using a plane diffraction grating. Okay, this is how the experiment is done. Then coming to the Fresnel's half period zones, each point in a light source sends out in all directions. According to the wave theory of light, each point in a light source sends out waves in all directions. Now the ether particles, as you can say hypothetical medium, are set up in vibrations. The locus of all the ether particles vibrating in the same phase is called as the wavefront. This is according to the Huygens Fresnel theory of propagation. According to Huygens Fresnel theory of propagation, the locus of all the ether particles vibrating in same phase is called as a wavefront. Coming to the Fresnel's half period zones, each point on the wavefront sends out secondary wavelets. Okay, Fresnel calculated the resultant intensity at point due to wavefront by dividing the number of zones, which are called as Fresnel's half period zones. Okay, he divided the wavefront in number of zones. Here you can see that this diagram, okay, where ABCD is a plane wavefront which is emitting a light of having wavelength lambda, and P is the point where the resultant intensity is to be calculated. So it is difficult as such that the Fresnel divided the wavefront into number of zones. Because it is difficult to find out the intensity at the point P, he divided the wavefront into number of zones, which are called as Fresnel's half period zones. So this theory is needful for in order to construct a zone plate. Coming to the next important topic, zone plate. The correctness of Fresnel's method of dividing a plane wavefront into half period zones, which forms the basis or for the proof of rectilinear propagation of light, can be verified. It can be verified by means of a device known as a zone plate. It can be verified by using a device called as zone plate. A zone plate is an optical device based on Fresnel's concept of division of plane wavefront into number of half period zones. It is specially constructed device having alternate bright and dark or you can say in interference you will say dark and bright. Here you can say transparent and opaque. Okay, transparent and opaque concentric zones. Then that device is known as the zone plate. Coming to the construction of the zone plate, a number of concentric circles whose radius is proportional to the square root of the natural numbers are drawn on the sheet of white paper. The alternate zones are painted black. The reduced size of this photograph is taken on a thin glass plate. The resultant glass negative is known as zone plate. Okay, the resultant glass negative is known as zone plate. The zones which are painted black originally appear transparent and others will be in black color. Thus, a zone plate allows light through alternate zones. Now, coming to the types of zones, the zone plate is divided into two types. First one is a positive zone plate and second one is a negative zone plate. In positive zone plates, a zone plate which will be having the odd number of zones are transparent and even zones are opaque are called as positive zone plate. Okay, odd zones are transparent and even zones are opaque. But coming to the negative zone plate, a zone plate which will be having odd zones as opaque and even zones are transparent is known as negative zone plate. These are the two types of zone plate. Coming to the working, let xy be the section of a zone plate. Here you can see xy is the section of a zone plate. Okay, then S is a source which is emitting monochromatic light of wavelength lambda. It will be emitting light of having wavelength lambda, which will be falls on the zone plate, and P is the screen where the diffraction is observed. Okay, P is the screen for the bright image. The distance between the zone plate and the screen is called by distance A, and the distance between the source and the so-called zone plate and the screen is given by B. Okay, the position of the screen is such that there is an increase in path difference of lambda by 2 from one zone to the next zone. Okay, there is an increase in the path difference. You can see here from PM1 to PM2 there is an increase in the path difference of lambda by 2, optical path difference. If you want specifically, it is a optical path difference. Now, by deriving these relations, by comparing this with the convex lens formula, 1 by f is equal to 1 by v minus 1 by u, where v is the image distance and u is the object distance, and it is compared with the 1 by v minus 1 by a, where v is the distance between the screen and the zone plate, and 1 by a is the distance between the source and the zone plate, is given by n lambda by rn square. Then the focal length of the zone plate is given by Fn is equal to Rn square by n lambda, where Fn is the focal length of this zone plate, Rn is the radius of the zone, n is the number of the zone, and lambda is the wavelength of the light, okay, wavelength of the monochromatic light. Thus, the zone plate behaves like a convergent lens. The zone plate will behave like a convergent lens. Now we are going to see what are the similarities and dissimilarities between convex lens and zone plate. Both the zone plate and convex lens form real images on either sides of the object. On other sides, you can say, other sides of the object, they will form images. Both the zone plate and as well as the convex lens possesses same relation between the object distance and the image distance. They have the same relation. Then the next point is the focal length. They depend on the wavelength. The focal length of both so-called zone plate and convex lens will depend on the so-called wavelength of the light lambda and possesses chromatic aberration. These are the three similarities between zone plate and convex lens. You can see in convex lens, focal length is directly proportional to the wavelength of light, whereas in the zone plate we will observe that the focal length is inversely proportional to the wavelength of the light. In convex lens, f directly proportional to lambda, but coming to the zone plate, f is inversely proportional to the lambda. The convex lens formula is given by 1 by f is equal to mu minus 1 into 1 by r1 plus 1 by r2, where f is the focal length, mu is the refractive index, r1 and r2 are the radius of curvature. But coming to the focal length of the zone plate, Fn is given by Fn is equal to Rn square by n lambda, where Fn is the focal length of the nth zone, Rn is the radiance of the nth zone, n is the number of the zone, and lambda is the wavelength of the zone. wavelength of the light. Okay. Coming to the dissimilarities, in a lens, image is formed by refraction. Okay, but coming to the zone plate, image is formed by diffraction. In convex lens, it is by refraction. In zone plate, it is called diffraction. In convex lens, all the rays travel same optical path before reaching image point, whereas path difference between the rays while meeting the position will be n lambda. In case of zone plate, it will be equal to the condition of n lambda. The image formed by a convex lens is more bright than the produced by a zone plate. In convex lens, it will be more bright as compared with the zone plate. Why? Because in zone plate, alternate zones only transparent and the alternate zones are opaque, right? For convex lens, FV is less than FR, but for the zone plate, FR is less than FV. Okay. Now, convex lens possesses only one focus on each side, while a zone plate possesses several foci. Why? Because the focus is directly proportional to the square root of the natural number. Each zone will have different focal lengths. Okay. These are the dissimilarities between convex lens and zone plate.